Welcome to Energy System Modeling course, exercise 3. Again, the exercises can be found from the Moodle folder, and in here you can see the PDF file. So let's go ahead and open that one. So in the folder, you can also see this household consumption Excel file. So there's household consumption and outdoor temperature data from 2023 and 24. And the household in this case is electrically heated. So we want to separate the heating electricity consumption from the overall consumption data for year 2023. And then we are going to make a model and predict the year 2024 and compare it against the measured values. So this can be done by achieving or this can be achieved rather by using a physical consumption model for the heating. So the extraction, that is. So what we're going to start doing in here in the beginning. So let's take the Excel out of here. So now I want to first plot these ones. So I'm going to select the power and the temperature for the year 2023. And I'm going to insert a scatter. Remember, not a 2D line graph, rather a scatter with points. And this seems that the values are in wrong order, so I'm going to head and switch those up. So x-axis is supposed to be the temperature, and y-axis is going to be the power consumption. So this is in kilowatts, and this is in Celsius. So let's go ahead and modify the chart a bit. So I'm going to use the quick layout again and remove the title and the grid lines. And then from the axis options, I'm going to say that the axis value that it crosses, it's going to be -30. So now it's a bit easier to read, and let's put black font again and a bit higher font size. So here is the power rather in kilowatts, and in here is the outside temperature in Celsius. And what I can also do is I can, from the marker options, we're going to say solid fill. We're going to ignore the line from the bound or the border, and then we're going to put some transparency. Let's put it a bit darker in here. So a bit transparency, so you can see that there's a lot of data in the middle part of this particle swarm. But we are interested in the outlier point, so the border of this one. And let's remove the border from this one so it's easier to look at. So at first, we're going to have a vector in here. So I want to find the points that are the lowest ones in here, because that's pretty much the baseline consumption that we're looking for. And that increases when the temperature decreases. So from that, we can deduce. Let's open up the whiteboard so I can draw on there. So from here, if we're going to make a fit for this one, we can see that there is the delta y, and here is the delta x. So based on that, we can derive a function for this q. So q equals UA delta t. And what we are after is pretty much this one, which is the slope. So this one. So let's go ahead and find those points. So I'm going to start from -30. And the next one is going to be -29. And let's go ahead and drag that up to, let's say, 30. It was a bit too far. So 30, somewhere here. And then we want to find the temperature points between these caps and find the corresponding values from the power consumption, and then we're going to get the minimum from that. That was a bit complicated formula, but in the beginning, we're going to write an if statement. So there's something times something, so that's basically the and function, and then something happens. So the first one, we're going to have to select the temperature values. So if some of these values is going to be above or equal than this, so if it's going to be above or equal 30, I'm going to go ahead and copy this one. And then if it's going to be below this one, so in between these values, these are going to be stay constant, and these are going to be rolling with the numbers in here. So then what happens? I'm going to find the power value from here. And this is the equation that does it. So if I were to press enter now, it's going to spill over into here, and everything is false because it doesn't find any values that are between 29 and 30. You can see that there is nothing in here. But now if I take the minimum out of these ones and double click it into here, and what I'm going to do is select another data set into here, starting from, let's say, this 20 to 20 maybe. Or actually we can take all of the points till 31, since there are points in there. So now what you're going to see is a plot that finds the lowest points of this particle swarm in here. So maybe I'll put the marker to red so it's easier to see and no line in there. So now we have some data to plot our line against, so we can use a linest function. So let's take these ones, and I'm going to move them a bit downwards and put equals linest into here. So let's start it from this minus 20 and maybe go up to, let's say, this 20. This affects the outcome to some extent. So actually that would have been the known x's, and this would be so known y's in the beginning, yeah, and this would be the known x's up till this point. And there's going to be calculated normally. So here, so there, this is the coefficient that is basically something that we can use as the UA. So we have a fit we can use to determine the heating electricity consumption for the household now. So we can go ahead actually and draw this curve in here. So I can draw it in a way that this coefficient, let's dollar that, times the outside temperature plus this coefficient. And we can go ahead and draw it in here. So let's say select the data from here. Again, X values are going to be the temperature values in here, and the Y values are going to be these ones in here. And now we can go ahead and remove the markers. So no markers and solid line. And let's make it a black one, smooth it with a little bit of dashing in here. And we can force the axes to be minus 30. And in here, it's going to start from 0. And these are coefficients that we can change. But basically what this tells so we could change these in order to change the slope in here, or the point that it touches to this y-axis. But now we have a physical model that we can use to subtract the temperature, or the rather heating related power consumption from here. So let's go ahead and insert a row in here. So I'm going to subtract from here minus this one times outside temperature plus this one. So now what's left is only household appliances in here. But if I were to draw this one, you're going to see there's negative consumption in here. And that's because that is because our model isn't perfect. In these cases, some of the values fall behind, or rather below the line in there. And now it seems that my Excel froze, so we're going to have to wait a while. Yes. So let's make an if statement. I'm going to copy this one, and I'm going to say if this one falls below 0, then you're going to give me 0. Otherwise, you're going to give me this one. Okay, so it was the other way around. This way. Yeah, now it's correct. So let's see. Now it cuts down all the spikes that were below 0. Okay, so this corresponds to the household appliance usage. And in ChatGPT, what we're going to do is we're going to make a probability density-based behavioral model. So what I've done in here is I prompted that I have a consumption data in Excel file. You want to be precise again in here. In Excel file called data XLSX, where the first column is hours of the year and the second column is power consumption. So that's the power consumption we just extracted. I want a Python code that reads the original data. The year starts on Sunday, so that was 2023. Again, you want to be exact because that matters. I want the code to divide the data into categories: season, weekday, hour of the day, and make probability functions for all these categories and predict the next year's consumption. Do it 3 times so we can see the effect of the probability functions. Write the data into results to XLSX. I already had one result file in my folder, so that's why I named it results2. And as you can see, this was the first code that came out with the prompt. And in here, you can see that it divides it into 4 different seasons. It's taking into account the weekdays, and then it takes into account the hour of the hour of the day. And in here, you can see it's clearly using the kernel density estimation. Okay, so let's go ahead and copy this code. So this one, and I actually have it in here, this household model Python. And then we want to open the data Excel file. So in here, I can put this code from here till here. So you can see it's the same code. And then let's open up the data Excel file. So here. And what we want to do is we want to copy this one into here. So it's slightly different in the previous time when I did this, I might have had a slightly different slope in the function. Okay, so these are hours of the year. So it goes up till 8,760. And this is the household appliance related consumption value. So that would be, for example, if you're heating up a sauna or using microwave or having the fridge on or television on and so forth. So we have that in here. And now it's going to make a probability probability function on with what kind of a probability, for example, during winter Mondays on 8 o'clock, do you have a certain amount of consumption? So let's go ahead and use that code and see what comes out. Fingers crossed that it works. Simulation complete. Okay, so let's go to results 2. And you can see it's updated it just now, 1632. So I'm going to head and open this one. So you can see in here, as I asked, there's 3 values for the consumption. And let's draw these. And you can see that it's rather good. But again, in here, you can see there's negative consumption values, and that's something that wouldn't be possible. But you could modify the code in a way that you could prompt, for example, that don't give me negative values. That's something you can modify in the code. But let's go ahead and use this anyway. And you can see that these are rather similar. You can clearly see that there's some difference between winter and spring and summer and autumn, and the winter begins from here as well. And seems that my Excel froze again, so we're going to have to wait a while. Okay, so let's go ahead and take some one of these values or value series. So for example, the second one, and we're going to copy it. Let's actually make some room maybe in here. So we want to have room for the, or actually in the code, let's do it in this way. I'm going to copy and paste it into here. So we're going to assume that in 2014, it's going to be similar behavior. So this also applies to 2014. So household appliance usage in 2014, household appliance usage in 2000, not 14, rather 24. And so we can parse together now the household appliance usage plus this value times temperature in 24 times this one plus this one. So now we have combined a data-driven probabilistic model with this physical model that takes into account the household heating. So let's go ahead and calculate the values. And then I'm going to make room in here for, so that's prediction 2024. And I want load duration curve, original and load duration curve for prediction. So the original is going to be done. So these are going to be done with the large function. The original can be found from here. So let's put dollars in there. And that's going to be the first and largest. And then I'm going to move it into, still going to be integers in here and the prediction in here. So let's go ahead and plot these ones. I'm going to plot something from here and move the series. It's easier like that. So we're going to make a scatter like that. And it seems that my Excel is freezing again. There's a lot of data to handle in here, so That's why it's taking a while. But as you can see, the prediction is matching pretty well the 2024 measured values. So we're going to just draw the log duration curves and see what's up. In here, there are values that are slightly below zero. Okay, so now it unfroze. So let's take this one to, let's make it the prediction. And the other one is going to be the original. And as you can see, we would have to correct our model in a way that it wouldn't make these smaller than zero values in here. So that's something you could cut out. But other than that, the load seems to be following the original rather well, or the measured one. So this was predicted based on 2023 and projected or predicted to 2024. So there you have it. We have a probabilistic model, data-driven one that is for the household appliance usage, and the household heating is a physical model. So let's go ahead and move on to the next assignment. So this was the one that we just did. And then we're going to move on to the district heating city file. So this is pretty much the same thing, but rather than doing a probability model, we're going to use some of the data to represent hot water consumption. So let's open this district heating file. And we have consumption in 21, consumption in 22, outside temperature 21, outside temperature 22. And what we need now is the hot water consumption, and then you have household heating consumption. So let's take the hot water consumption and let's subtract it from this 2021 and make the physical model again. And then we're going to test it on this 22. So if you were to draw this one, you're going to see how the city, so insert and scatter, this line scatter, you're going to see how the city district heating consumption profile follows this seasonal patterns, and also you have this variation in here due to the temperature changes. So in here, we can assume that there is no household heating. So let's let's make a similar curve as before, but now in the beginning we have to subtract the hot water heating from the entire series. So let's examine, for example, week 25. So if I were to start from week 25, I'm going to say the hours of the year during that time is going to be 7 times 24, so that many hours in a week times 25, 4,200. And then I'm just going to see 24 times 7 times 26. So it's going to be 168 hours that we have to inspect. So let's go ahead and start from here. And there's this fill series, columns 168 with step value of 1. It goes until 168. And now we can add 1 always into the previous one. And then let's use the lookup function. So we're going to see this value from here, these two columns. So it's going to find the first column value, and it's going to return us the second column. And it's going to be exact match, so 0. And I'm still going to have to dollar these ones. So F4 and F4 in here. So now what it found for us is, let's take this one and draw it. insert and these ones. So this can be deleted. We have now here the hot water consumption during one summer week. And you can see it might be so that this is Monday, Tuesday, Wednesday. I'm not sure where the year started, but these would appear to be Saturday and Sunday. So what we want to do is we want to make a fit to describe this one. You wouldn't have to actually do that. You could take some average values out of the here or make a smooth out of this one. But I want to make these analytical functions, analytical fits, and let's use normal distribution for that. So for that, we're going to move these ones a bit lower because we need something. And by the way, we need the hours of the day only. So let's make here equals mod. So number is going to be this one minus 1. The divisor is going to be 24 and plus 1. So what this does is it goes up till 24, starts all over again, 24. So that's the hours of the day. So mod this number minus 1, divisor 22, rather 24 plus 1. And then we're going to have a normal distribution. The things what we need is we're going to need a baseline, so base, and multiplier. Multiplier is going to be here. So let's put baseline. So that means it's going to be somewhere around 40. The multiplier, let's put 15 in the beginning. And then if we see normal distribution from here, normal dot dist, you can see there's means and standard deviation. So we have to have, let's put X from, or S from there rather. And this is mean, and this is ST deviation. And let's put mean to 5, and this to maybe 2. And we're going to need 2 of these values. So this indicates at which point this first hump is and the second hump. So let's put the other one to, let's say 15, and this is going to be 3 perhaps. And now I'm going to build up the function, and let's see, we're going to need to plot that one as well. So I'm already going to put something in here so you can see it. So let's put something multiplied with this one plus the baseline. So those are constants. And in here, inside, we're going to have normal distribution plus another normal distribution. So normal distribution, this is going to refer to the hours of the day. So X is in here. Mean is going to be this one, and standard deviation is going to be this one. And the same thing goes for the next one. So normal distribution, X is going to be this one, mean is going to be this one, and standard deviation is going to be this one. And now it's complaining about the value that I forgot. So it's going to be probability mass function. So false or 0 into here. You would put 0 like this. And these are in dollars in here. So let's see. Must have missed some parentheses. So let's see that this is correct. So this one is, yeah, there seems to be some parentheses missing from here. So now this normal distribution, actually one parenthesis missing still. Yeah, like that. And one normal distribution in here. Actually, I can probably take one of these ones off. Yeah. So there's the first, there's the second, it's multiplied and added with the baseline. like that. You can do these spaces in Excel to make it a bit easier to read this formula. Now let's multiply this formula. And as you can see, we have these humps or lumps in here as well. So we can multiply it a bit further. So let's multiply 60. These could be, let's see what it does. That makes it a bit more spikier. So let's these ones into here and multiply it a bit further. This could be moved a bit the other way into here, and this one as well. I'm going to move it like that. So you can see it starts to resemble the shape that we want. So we want to make a fit that kind of resembles these values over 1 week. So we don't want just 1 day. So we want 1 week. Let's use the least square error method. So what I'm going to do is I'm going to press equals this one minus this one. So the difference between the data point in here and in here, for example, to the power of 2. So that's the square error. And we're going to sum that up. So error in here is going to be sum of the square errors in here. And then you're going to use solver. And how you can access solver is it's in the data tab. And if you don't have it in here, you can press file, options, add-ins, Excel add-ins, and go, and you can untick or rather tick it from here. So from a default user, it's unticked, and then it should appear in here. So solver, yes, solver is a tool that we can use to make multi-objective optimization. So I'm going to reset everything, and I'm going to press this error cell, and we're going to minimize it. We're going to minimize it by changing all of these 5 cells. So goal seek can be used to change or optimize single variable, and this can be used to change all of these to minimize this. So let's go ahead and solve it. So you can see the iteration goes smaller in here, and that seems to be a rather good fit. So now we have the parameters to describe our hot water consumption. And since during the summer there is no household heating, we're going to assume that during the whole year, the pattern is going to be somewhat this. So I'm going to use these values to subtract the hot water consumption from the household heating. So this is the entire city in here. And you can see the consumption is hundreds of megawatts. And again, in here, hot water consumption, some 60 megawatts. So let's go ahead and make a line in here. So, and again, we are going to take this function from here. I don't want to write it again. So what we can do is copy and paste it here, and I'm just going to move these ones into here. So that's the hour of the day. And these ones remain constant. So we have a constant, this wavy function in here. So all of this can be subtracted from the overall consumption. So now what we are left is just the household heating. And in a similar manner as before, in the previous exercise, I'm going to select all of these values and the outside temperature from here. And I'm going to make a particle swarm. And again, these are the wrong way around, so I have to use or move this one in here and this one in here. And let's make it a bit nicer, and I'm going to make some room for it in here. So let's see if I can insert some values into here. Like that. A couple of more. And again, this one, we're going to format the axis in a way that it's going to cross in -30 and then put a quick layout elements into there. And from there, and in here, there's the just going to put temperature T and consumption. Well, let's put Q in here, consumption in megawatts, like that. And as you can see, if I were to draw it against this original data, it's going to be more upwards. But if I put it in here, again, our model isn't exact, and that's why some of the consumption values goes negative. What we could do is use a similar technique as before. So we could take, for example, -30, -29, the values up till, let's see, drag and drop till 30. And then let's go back to the other file and copy this, rather this one from here. Back to here, and then we have these values in here. So this was 30 and 30. So temperature should be the blue one, outside temperature in here, and then it's going to return the consumption values and get the minimum out of them, like that. So if I were to draw those in here, select data, we're going to add a series. X values are going to be rather from 29 till here and till here. And by the way, you can see that it's not matching exactly the lowest values, since these are integer numbers rather than the ones that it's actually finding from there. But either way, that's close enough for us. And now I think it's more important to have this marker fill with transparent. Okay, let's take out the border from there. Yeah. So now you can see that there is actually a certain amount of points that are kind of outliers. So there's very small amount of points in here. So when we are making the linest function and getting the slope for it. So let's make it again, linest equals linest from this -21. Let's take it till 20. So that's the known y values. So it should be in here, and the known x's should be in here. And if I'm going to draw the line, so outside temperature times this one, and this is for the entire city, the UA value. So this contains the information of collective average overall heat transfer coefficient times the surface area of the buildings, and plus this one. So it can be used for the entire city. And then let's draw the line. So selecting from here, -29 till the very end. Oh, that was the name of the series. So from here and from here. And it named our series rather funky in there, but oh, so let's do that again. Let's do that again. So I'm gonna erase those ones and again select data, new one, and now the x values from here till here, and then the y values from here till there. And let's remove the markers and let's put a solid line that's going to be black and it's going to be dashed like that. Okay. And we don't have to draw it all the way down there. But now you can see that it's really on the bottom part. So I would say that in the citywide inspection, what we could do is we could modify these ones a bit. So I'm going to put -15 in here and 250 maybe in here. And I'm going to change these ones into here. So it modifies that one a bit. Let's see if I'm going to put 300, it's going to bring it upwards. So let's put 270 maybe. 270 might be a bit much. So 260, something like that. So it doesn't exactly go through the entire particle swarm. Let's see, this one still 15. No. It's hard to see when it's bouncing around. But let's let's try with this one. So the point at which it would hit x-axis in here is 16 and 25. So after that, it wouldn't have any building heating, and that sounds about right. That's the 17 degree mark. So let's try and build the model. So let's make again some room room in here. A couple of ones in here. Oh, shrunk it down too much. Yeah. So prediction 2022 now. And the original is in there. So we're going to add outside temperature times this one plus this one. That's going to be constant. And then I'm going to have all of this one, the normal distributions added into here. So I'm adding the outside temperature based heating demand and the time series based estimation of the hot water demand. So let's see how it looks like. That's the prediction for 2024. And now let's have a graph out of it. We're going to insert this one. So there's one curve, so let's have another. So what I did in here now, and again, the Excel seems to be freezing. So what I'm doing is I have one series in here. I'm clicking from here and not moving anything. Control C, Control V. So it adds one series on top of it. And now what I can do is just drag and drop. I can drag this one to consumption 2024, and I can take the other one and drag it till 2000, or rather 2022. And as you can see in here, we have these negative values. And that's because nothing is telling our consumption or the building heating consumption model that don't go up till here. So what we can do to correct that is we're going to insert a modified temperature value in here. So if outside temperature is going to be above, actually we're going to have to calculate the value in here. So this one divided with minus this one. That's the point at which it hits zero. So if this one is going to be above this one, we're going to dollar sign it. Just give this one. Otherwise, give the original value. So now it's going to cut out the values from here if I'm going to move the temperature up till here. And there you have it. Now there's a lot of oscillation in here. And that is due to the fact that we didn't take into account the thermal inertia in there. And if in the article that I listed into the original or the assignment rather in here, this city scale transient district heat demand by combining physical and data-driven approach. So this is exactly what we did, but we did a modified, easier version of it. So they took into account the thermal inertia of the buildings as a whole. But that's something that we're going to not add into here. But let's still check the load duration curves. So load duration curve, original, and load duration curve predicted. And again, it's going to be the large function, large. So original data is in here. And this is going to be 1. And I'm going to dollar this one and this one. And then let's take Control C out of here and Control V into here and copy this one into the prediction. So predicted. Let's put it to predicted load duration curve. Yeah. And the other one is going to be this one. So you can see it's not such a good fit. What we could do is we could modify these ones. So let's say if we were to use this exact values from here, would it make it any better? Seems that it makes it a bit worse, and that's why I think this assumption that you can bring this curve upwards a bit. So let's put 2070 into there. Wonder which direction should I put this one. So yeah. So that would be kind of calibrating the model. But it seems that it's a-okay of a fit. It's just that you're going to have to adjust these parameters in here because there can be such points, especially because of the thermal inertia in there, that that our heating consumption isn't this low. So you can increase this UA function from there. But yeah, you can tweak and adjust the model, but there's an example how you can determine the district heating consumption profile for next year, or rather not profile, but time series. So you can use a combination of this physical model and data-driven model. And in the previous example with the household, we were using this probability density function to predict the values for the household appliance usage. So that wasn't as smooth of a data set as in here. As you could see, that this follows a rather nice trend in here. And that's because this data, the original data, is aggregated. Okay, so that is the exercises for this time, and you can see this article if you feel like you want to go into a bit deeper into this subject.